So far, we have discussed the mean temperature difference method for analyzing heat exchangers. We derived expressions for the mean temperature difference in various flow arrangements, for various flow arrangements like parallel flow, counterflow, all the three cases of cross flow. And once we had those expressions or the results in the form of graphs, we were able to show through numerical examples how one does calculations using the basic performance equation Q is equal to U A delta T m. Now, today we will look at another approach. We will discuss a method called the effectiveness NTU method. We are going to discuss a method called the effectiveness NTU method. Now, first of all, I want to describe the types of problems that we encounter and why the effectiveness NTU method is at all thought of. So, let us first of all just state two types of problems that we generally encounter in the case of heat exchangers. Generally, we encounter two types of problems. And these problems are as follows. In one type, we are given two fluids we are given the flow rates and the inlet and outlet temperatures on the two sides, that is m dot h T h I T h e, m dot c T c I and T c e, given the flow rates on both sides and the inlet and outlet temperatures on the two sides, and we are given the value of u. All these quantities are given to us and we are asked find the value of A. What is A? That is a typical problem, and that is the type of problem which we have done in the previous lecture. Let me just outline this a little, so that it is seen clearly. We are given the data, which I am going to just put a red boundary on it, red lines around it. This is the data given, and we have to find the area A of the heat exchanger. This is one type of problem. I call this as, let us say, call it type 1. And as I said, we have already solved problems of this type using the mean temperature difference approach with no real difficulty. The second type of problem, let us call that as type 2. We are given, in the second type of problem, we are given two fluids. When I say two fluids, it means we know the properties of the fluids. We may need the specific heat or whatever other properties might be needed, density, etc. So, we are given two fluids. We are given a heat exchanger A. We are given some heat exchanger whose area is specified, a heat exchanger whose area A is specified. We are given the flow rates on the two sides, m dot h and m dot c, and we are given the inlet temperatures on the two sides, T h I, T c I, and we are asked to find the outlet temperatures on the two sides, T h e, T c e. That is the second type of problem, and let me again just outline, put a red boundary around it to show that this is the second type of problem we are talking about. Given two fluids, given a certain heat exchanger with an area A and given two fluids entering with flow rates m dot h and m dot c and two inlet temperatures Thi and Tci, what are the exit temperatures of these two fluids? So, if you want to describe in words what these two problems are, type 1 is a problem in which we are sizing the heat exchanger for a given job. We are wanting a certain amount of heat to be transferred and we are saying what is the area of A required for this job. Type 2 is a problem in which we are given a heat exchanger of a certain size and we are asked to calculate its performance for certain given inlet conditions and flow rates, inlet conditions of temperature and flow rates. Now, let us try to apply the mean temperature difference approach to both these problems. For the first type of problem, apply the mean temperature difference approach for both these problems. For the first type, our basic equation is Q is equal to U A delta T m, and if I want to calculate the area A, I will say A is equal to Q upon U delta T m. And in the previous lecture, we have done such problems by the mean temperature difference method. We have calculated the mean temperature difference depending on the flow configuration. Once we have got it, we have used this basic equation to get the area A of the heat exchanger. Now, let us look at the second type of problem. For the second type of problem, if I put down again my basic equation, basic performance equation, Q is equal to U A delta T m. Well, you can see U is known from my knowledge of convection, A is known because the size of the heat exchanger is given, but Q, in order to calculate Q, I will need an exit temperature on one side or the other, that is not known, and delta T m cannot be calculated because both the exit temperatures are not known. So, both Q and delta T m are unknowns in this equation, and we will need a trial and error approach to solve this type of problem. What do I mean by trial and error approach? What I mean is the following. Assume, let us say, a value of one of the exit temperatures, THE. The moment I assume THE, I can calculate TCE by heat balance, because the heat transferred from the hot side is equal to the heat gained by the cold side. So, if I assume one exit temperature, the other can be calculated. Once I get both the exit temperatures and I know both the inlet temperatures, I can calculate delta T m. Then I see from my basic equation whether Q is equal to U A delta T m, whether Q, the left hand side, is equal to the right hand side. If it is not, go back and assume some other value of TCE. So, I will need a trial and error approach, guess value of TCE, go through the calculation, check if the left hand side is equal to the right hand side, otherwise go back again. Now, the trial and error approach can be avoided if we adopt the effectiveness, the alternative method, which is the effectiveness NTU method. So, one reason for introducing this new method is that we do not need a trial and error approach for this second type of problem. So, let me write that down. The trial and error can be avoided if we adopt the alternative method called the effectiveness NTU method. The trial and error can be avoided if we adopt the alternative method called the effectiveness NTU method. So, now let us look at what this method is all about. So, this is one reason why we are looking for an alternative method, that for certain types of problems the Q equal to U A delta T M method would require a trial and error approach. Effectiveness NTU approach would not require a trial and error approach. But that is not the only reason, by the way. The effectiveness NTU method has some other advantages. It is a dimensionless way also of looking at the performance of a heat exchanger, and dimensionless approaches always have certain benefits compared to dimensional approaches. So, that is also an added reason why we develop this new approach called the effectiveness NTU method. Now, let us start with the method. The first quantity, we want to define a quantity first called the effectiveness. We say the effectiveness of a heat exchanger, the effectiveness of a heat exchanger is equal to the rate of heat transfer in the heat exchanger divided by the maximum possible heat transfer rate. That is what how we define the effectiveness of heat exchanger. The actual rate of heat transfer in the heat exchanger divided by the maximum possible heat transfer rate. We will use the symbol epsilon for effectiveness. So, we will say epsilon is equal to Q, the heat transfer rate in the heat exchanger, divided by maximum possible, which we will call as Q max. Now, what is Q? Q is nothing but m dot H Cph into Thi minus The, or it is m dot C Cpc into Tce minus Tci, that is the loss in enthalpy on the hot side, the gain in enthalpy on the cold side. So, the numerator can be specified either in terms of the hot side flow rate and its change in temperature, or the cold side flow rate and its change in temperature. Both are equivalent expressions. Now, in the denominator, notice what we have put down is m dot Cps multiplied by Thi minus Tci. Thi is the entering temperature on the hot side, Tci is the entering temperature on the cold side. These represent the maximum and the minimum temperatures in the heat exchanger. Let us say, if I draw a scale here, this is Thi and this is Tci. This is where the hot, this is the temperature level at which the hot fluid enters, this is the temperature level at which the cold fluid enters. All other temperatures in the heat exchanger must be within this range. So, Tce or The have to be within this range, obviously. The maximum possible heat transfer rate therefore is obtained if I get the change of temperature of one of the fluids to be Thi minus Tci. So, I say all right, what is the maximum possible change of temperature in the heat exchanger? Thi minus Tci. And what flow rate and heat capacity do I multiply it by? I must multiply it by the lower of the two m dot Cp's, that is I have m dot H Cph, m dot C Cpc. The smaller of the two is what I need to multiply it by, not the larger of the two to get the maximum. Note that. Why is that so? If I take the larger of the two, S stands for the smaller of the two m dot Cp's. If I take the larger of the two, you will quickly find out that either The or Tce will lie outside this band of Thi to Tci. Keep that in mind. Take any situation, specify two values of Thi, Tci, all right. Take some values of m dot H, m dot C. Take the larger of the two here, and you will quickly see, if I take the larger of the two in the denominator, you will either THE or TCE will lie outside this band. They will not lie within this band, which is an upper and lower limit for temperatures in the heat exchanger. So, Q max is equal to the smaller of the two m dot Cp, smaller of the two means calculate m dot H Cph, calculate m dot C Cpc, the smaller of the two is m dot Cps multiplied by the maximum possible change in temperature, that is Thi minus Tci. So, that is how we define the term called as effectiveness. Now, let us say that m dot H Cph is less than m dot C Cpc. Let us say we have a situation in which m dot H Cph is less than m dot C Cpc. Therefore, then m dot H Cph is equal to m dot Cps. It is the smaller of the two, so it is m dot Cps. In that case, looking back to the definition, you will see quickly epsilon becomes equal to Thi minus The divided by Thi minus Tci. That is our definition of effectiveness. On the other hand, if m dot C Cpc is less than m dot H Cph, then m dot C Cpc is equal to m dot Cps, and the definition of epsilon becomes equal to Tce minus Tci divided by Thi minus Tci. That is our definition of effectiveness. So, depending upon which is the smaller of the two heat capacity rates, m dot H Cph or m dot C Cpc, we will get this definition of effectiveness or this definition of effectiveness. Note, the two definitions are equivalent when m dot H Cph is equal to m dot C Cpc. Why? Because then Thi minus The will be equal to Tce minus Tci. So, it does not matter which definition you use, they are equivalent. Also note, by definition, this is one thing to note. Second thing to note is, by definition, epsilon is dimensionless and epsilon is a number which is by definition bounded between 0 and 1. 0 less than or equal to epsilon, less than or equal to 1. So, epsilon is a dimensionless quantity telling us something about the performance of the heat exchanger, and it must lie between 0 and 1, because in the denominator we have the maximum possible heat transfer rate in the heat exchanger. So, now we have defined a term called the effectiveness, and what we are going to do next is the following. We are going to say, all right, suppose I have a parallel flow heat exchanger. Let us say I have a parallel flow heat exchanger. I want to derive an expression for the effectiveness of a parallel flow heat exchanger. Derive an expression for the effectiveness in parallel flow. So, let us start. Let us say assume m dot H Cph is equal to m dot Cps. All right. Then it follows that epsilon is equal to Thi minus The divided by Thi minus Tci. That is the definition if m dot H Cph is the smaller heat capacity rate. multiply the numerator and denominator by, in this case by 1 plus m dot h Cph divided by m dot c Cpc. So, multiply this by 1 plus m dot h Cph upon m dot c Cpc and divide by, I can always do that, 1 plus m dot h Cph upon m dot c Cpc, multiplying and dividing by the same expression. Now, this is equal to, now multiply this in, Thi minus The into 1 gives me Thi minus The upon Thi minus Tci. I am multiplying by 1, then multiplying Thi minus The upon Thi minus Tci into m dot h Cph upon m dot c Cpc. The two numerators multiplied, Thi minus The into m dot h Cph is q, q divided by m dot c Cpc is Tce minus Tci. So, I can say this is plus Tce minus Tci divided by Thi minus Tci. The whole thing divided by 1 plus m dot h Cph upon m dot c Cpc, which I can further write as equal to 1 minus The minus Tce little divided by Thi minus Tci, the whole thing divided again by 1 plus m dot h Cph upon m dot c Cpc. Now, if you go back to our derivation of the mean temperature difference in parallel flow, if you go back to our notes there, you will see we derived an expression at that point based on the integration which we performed there. We had an expression for delta Te by delta Ti, and the expression which we had derived earlier was The minus Tce, that is delta Te, upon Thi minus Tci, that is delta Ti, is equal to the exponential minus 1 upon m dot h Cph plus 1 upon m dot c Cpc. We had derived this earlier. If you go back to your notes, you will see this derived earlier. When we were getting the expression for delta Tm in parallel flow. So, now substitute this expression into the one above for epsilon, and we will get, substituting, we will get epsilon is equal to, substituting, we will get epsilon is equal to, I will do a little, I will put it in its final form, 1 minus exponential minus 1 plus m dot h Cph m dot c Cpc, the whole thing multiplied by UA upon m dot h Cph one plus m dot h Cph upon m dot c Cpc. This is the expression you will get. I have skipped a line or two of algebraic simplification. So, this is the end result that we are getting. Now, suppose we had initially made the reverse assumption. If we had assumed, initially m dot c CPC equal to m dot CPS. Suppose we had taken it to be the smaller, then we would have got epsilon is equal to the expression, and that you can verify yourself by going through the derivation. You would have got 1 minus e to the power of minus 1 plus m dot c CPC upon m dot h CPH UA upon m dot c CPC divided by the whole thing divided by 1 plus m dot c CPC upon m dot h CPH. So, we will combine both these now, rather than writing two expressions we will say combine the two expressions. We combine the two expressions for epsilon, and we say epsilon is equal to 1 minus exponential of minus 1 plus m dot CPS upon m dot CPB, that is the larger of the two, multiplied by UA upon m dot CPS the whole thing divided by 1 plus m dot CPS upon m dot CPB. So, m dot CPS is the smaller of the two heat capacity rates, then m dot CPB is the larger of the two. This way we have written one expression for both the, instead of two expressions for epsilon for the two different cases. All right. Now, let us now define two new dimensionless parameters. We are going to define one, first of all, a parameter called as the capacity rate ratio, for which we will use the symbol capital C. And second, we are going to define a dimensionless parameter called the number of transfer units, for which you will use the symbol NTU. C is defined as the smaller of the heat capacity rates divided by the larger of the heat capacity rates, m dot CPS upon m dot CPB, and NTU is defined as UA upon m dot CPS. So, note, you will note by definition that first of all, for these two dimensionless parameters, you will note both are dimensionless. Let me write that down to emphasize the point. Like epsilon, these two parameters are dimensionless also. Also that the quantity, the parameter C is dimensionless and has to be between 0 and 1, 0 less than or equal to C less than or equal to 1, and NTU is a positive dimensionless number which can be any number greater than 0. Right. So, we have defined two further parameters, and our whole performance now of the heat exchanger is going to get defined by these dimensionless parameters. Now, put in these definitions. Put these definitions into the expression for parallel flow, the definition of C and the definition of NTU. Put these in, and what do we get? We get a nice, neat, simple expression. We get the expression, let me show that, said for parallel flow, epsilon is equal to 1 minus, for parallel flow, epsilon is equal to 1 minus e to the power of minus 1 plus C into NTU divided, the whole thing divided by 1 plus C. you get a nice neat expression. The whole performance of a parallel flow heat exchanger is expressed in terms of 3 dimensionless parameters epsilon, C and NTU, very neat expression for the effectiveness. Suppose I were to plot this, what would I get? I would get something like this. Suppose I were to plot effectiveness against NTU with C as a parameter. C can range between 0 and 1. So, notice for C equal to 0, I would get a line like this with effectiveness increasing with NTU, and then asymptotically going into 1. Then for C equal to 0.25, again effectiveness increases with NTU and asymptotically goes into a value of 0.8. So on at C equal to 1, that is when both the m dot Cp's are equal, the effectiveness increases with NTU and asymptotically goes into a value of 0.5. This is 0.5 here. So, in each case the effectiveness increases with NTU and then asymptotically goes into some particular value depending on the value of C. Whether C is 0, it goes into 1, asymptotically into 1, C is 1, it asymptotically goes into the value of 0.5. And this graph, I mean this expression that we have derived for parallel flow is now shown graphically in this form. We could do the same thing for counterflow as well, and I am not going to go through that whole derivation. I leave that as an exercise for you. Exactly along identical lines, start with the definition of effectiveness, take one of the m dot Cp smaller, go through the whole process, you will get the expression which I have shown here at the bottom for the effectiveness in counterflow. You will get in counterflow, you will get effectiveness is equal to 1 minus e to the power of minus 1 minus C into NTU divided by the whole thing divided by 1 minus C into e to the power of minus 1 minus C NTU. This is the expression, and I would like you to derive this on your own. So, now we have got effectiveness as a function of NTU with C as a parameter. That is what we have got graphically, and let me show what it looks like in the case of counterflow. This is what it will look like in counterflow. The effectiveness increases with NTU for any given value of C, C equal to 0 asymptotically goes into 1. For C equal to 1, it also goes on increasing, and the NTU is large enough, then this value of epsilon will eventually go into 1. It will take a long time, but will eventually go into 1. So, in the case of counterflow, the effectiveness asymptotically goes into 1, but with C equal to 1 or C equal to 0.75, you need very large values of NTU to asymptotically go into 1. Such values are normally not used in practice, where we generally have heat exchangers with NTU ranging from 0 to about 5. That is why this graph is stopped at a value of 5 here in this case. So, these are the same expression, the same equations plotted graphically. Now, the same calculations have also been done in cross flow. Now, mind you, in cross flow you cannot derive a closed form expression like we derived in parallel flow or counterflow. In cross flow you have to do numerical integrations. This has been done for cross flow for all the 3 cases that we have described, both fluids unmixed, one fluid mixed, the other unmixed, and both fluids mixed. And the expressions for have been derived, I mean the calculations have been done numerically, and the effectiveness against NTU graphs are as you are seeing them here. This is the case of both fluids unmixed in cross flow, effectiveness plotted against NTU, effectiveness goes on increasing depending on the value of C, and asymptotically goes on approaching some high value as the value of NTU increases. This is the case of both fluids unmixed. The next graph I am showing you is effectiveness against NTU for the case of one fluid mixed and the other unmixed. This is the second case of cross flow, and the third case of cross flow is when both fluids are mixed, that is this one, and in this case you can see that the values of effectiveness do not asymptotically go into 1 as NTU goes on increasing. I will not spend time explaining that, it is not necessary. It is important that you should know that these graphs are available plotting effectiveness against NTU, and we will use them just now for solving one particular problem. Now, a special case again, which we have discussed earlier in the case of mean temperature difference, but I would like to discuss again. Suppose the capacity rate on one of the sides, hot side or cold side, is infinite. Capacity rate m dot Cp is infinite either on the hot side or cold side. It follows immediately C is equal to 0, because the denominator is going to infinity in the definition of C. For this situation, you can show that for all flow arrangements, epsilon is equal to 1 minus e to the power of minus NTU. You get this nice simple relation between effectiveness and NTU when C is equal to 0. So, keep this in mind that for this special case, it does not matter what is the flow arrangement, you get the same value of effectiveness. And you will recall from our delta T m discussion that I had said to you then that the delta T m when C is equal to 0, the delta T m is the same whether you have parallel flow, whether you have counterflow, or whether you have cross flow. Now, let us do a problem, a numerical problem, so that we get these ideas straightened out. The problem we are going to do to illustrate the use of the effectiveness NTU method is the following. We say in a gas turbine power plant, heat is transferred in an exchanger, in a plate fin heat exchanger, heat is transferred in a plate fin heat exchanger from the hot gases leaving the turbine to the air leaving the compressor. We utilize the energy available in the exhaust gases of the turbine to heat up the air which has just been compressed before combustion takes place. This helps to increase the efficiency of the gas turbine cycle. Given the air flow rate, is 5000 kilograms per hour, and the flow rate of hot gases is a little more than that because of the fuel added on at the time of combustion. So, 5075 kilograms per hour. Further, given THI is equal to 450, the hot gas is leaving the turbine, the air which is to be heated up, inlet temperature is 170, the value of U is 52 watts per meter squared Kelvin, the value of A is equal to 50 square meters, Cp on both sides is equal to 1050 joules per kilogram Kelvin. This is given. Now, further given that the flow arrangement is single pass, cross flow with both fluids unmixed. A plate fin heat exchanger with fins on both sides would ensure this, both fluids unmixed. Now, this is the arrangement. It is a plate fin heat exchanger, single pass cross flow, both fluids unmixed, inlet temperatures and flow rates given on both sides. Find the two exit temperatures. Find THE, find TCE, find the quantity of heat transferred in the heat exchanger. This is a problem which it would be ideal to solve by the effectiveness NTU method. You will agree on that. And just to refresh your idea, here is the core of a plate fin heat exchanger, which I am showing you just now. All right. So, one fluid will be entering through these passages, say let us say the air or the hot gases, the other fluid will be entering through these passages. So, you have got a situation of cross flow, both fluids unmixed because of the fins which are in the parallel plate channels. That is the what I want you to see. So, the fins ensure that both fluids stay unmixed on both sides. Okay. Now, let us apply the effectiveness NTU method to this. So, let me just draw a sketch of what we have before us. It is useful always to put down the given numbers in a sketch. So, we say here is the heat exchanger, let us say this is the area A of the heat exchanger, 50 square meters. Then we have the fluid to be heated at 170 degrees centigrade and its flow rate m dot c is 5000 kilograms per hour. We would like to find out its exit temperature, and on the other side we have the hot side inlet temperature 450. These are the hot gases leaving the turbine after expansion. The flow rate on the hot side 5075 kilograms per hour, and we would like to find out the exit temperature on the hot side THE, TCE and THE. So, let us get the quantities now. C, the capacity rate, is equal to m dot Cps upon m dot Cpb. M dot Cps is obviously on the cold side. So, it is 5000 into 1050 divided by 5075 into the specific heat happens to be the same on both sides, which is so we get 0.985 to be the value of C. NTU is equal to U A divided by m dot Cps, that is 5000 upon 3600, so many kilograms per second, into Cp 1050, which gives me 1.783. Now, go to the figure for effectiveness against NTU with both fluids unmixed. You recall we had shown that figure, and let me just show it to you again. This was the figure that we had, effectiveness against NTU, both fluids unmixed. We go to this figure, and in this figure which I have shown you, in this figure we will have to do a little interpolation. This is our figure, cross flow, both fluids unmixed. For this is NTU and this is epsilon. We will have to go to the graph for C equal to 0.985. There is a graph for C equal to 1. So, we will have to go a little below it, and then NTU is equal to 1.783. So, we say all right, 1.783 NTU, and its intersection with C equal to the graph for C equal to 0.985 would give epsilon is equal to 0.60. So, from the figure from the results in the figure, the graphs in the figure, for cross flow both fluids are mixed, we get epsilon is equal to 0.6, and epsilon in this case is nothing but TCE minus TCI upon THI minus TCI. So, if I substitute the numbers, I will get TCE minus 170 upon 450 minus 170, and I get on calculation TCE is equal to 168 plus 170, which is equal to 338 degrees centigrade. I get Q, which is nothing but the heat transferred, 5000 upon 3600, that is the flow rate in kilograms per second, into 1050 multiplied by the change in temperature 450 minus 338 minus 170, yes, change in temperature on the cold side, that comes out to be 245,000 watts. And finally, I have to calculate THE, which I can just get from a simple heat balance from the two sides. Heat gained by the cold side is equal to heat given up by the hot side. So, I get 5075 multiplied by the specific heat 1050 multiplied by 450 minus THE, this is Q, is equal to 5000 multiplied by 1050 multiplied by 338 minus 170. So, I get THE minus is equal to 284.5 degrees centigrade. So, these are the four answers. We have got THE, the one exit temperature, and from the previous page if I go back, we have got the other exit temperature, and this is the heat transfer rate Q, so many 245,000 watts to be the change in to be the heat transferred in the heat exchanger. So, these are the three answers that we were looking for. Now, mind you, if we had adopted the Q equal to UA delta Tm approach, we would have needed to do a trial and error in this case. That is a good reason why we have adopted this particular method. Now, before we close this topic of heat exchangers, I have discussed both the methods, which is what we wanted to do. Let me say that heat exchanger design is not just a matter of applying the Q equal to UA delta Tm equation or effectiveness NTU. There is more to it. There are many more other considerations in designing heat exchangers, and I just want to list them for you, not really take them up in any detail. So, here are some other considerations. Other considerations in designing heat exchangers. Look at this: pressure drop on either side. It is a very important consideration. Sometimes there are restrictions on how much should be the pressure drop. Sometimes size restrictions are there. The heat exchanger should be of a certain size. Very often stress considerations are very important. There are high temperature changes in the heat exchanger. It is a pressure vessel, you have to design it according to pressure vessel code. So, stress considerations are extremely important to ensure that the heat exchanger stands up to the required stresses, either mechanical stresses because of pressures or thermal stresses because of temperature differences. There are servicing requirements. We have talked of fouling. Now, if fouling takes place, you must be able to clean the heat exchanger. So, servicing requirements means you must be able to open out the heat exchanger and be able to clean it effectively, not keep it out of service for too long. Materials of construction are very important. If you do not use the right materials, the heat exchanger may corrode rapidly, erode rapidly, whatever it is. Materials of construction are important. Then you have to keep in mind system operation. What do we mean by that? Heat exchanger is part of a whole system, it is never working in isolation. Sometimes transients come into a system. We would like to ensure that the system operation means that the heat exchanger works as part of a whole system. And finally, of course, every heat engineer has to worry about the cost of a heat exchanger as part of an overall system. So, keep in mind that there are many other considerations apart from thermal considerations which go into designing heat exchangers. The pressure drop on either side, size restrictions, stress considerations, servicing requirements, materials of construction, system operation and cost. Now, let me just quickly review the main topics that we have done in this, the main subtopics that we have done in this overall topic of heat exchangers. So, let us just do a 2-minute review. What have we covered in this topic on heat exchangers? These 4 lectures that we have had. First of all, we, if you recall correctly, we discussed various types of heat exchangers. Then we said we will focus on the direct transfer type. And in the direct transfer type of heat exchanger, we described tubular heat exchangers, plate heat exchangers, extended surface heat exchangers. Then we talked about classification by flow arrangement. And you will recall here that we talked about parallel flow, counterflow, and cross flow, in which again we had 3 cases for consideration. Case 1, both fluids unmixed. Case 2, one mixed and the other unmixed. Case 3, both fluids mixed. Then we talked about the overall heat transfer coefficient and the fouling factor. How fouling is taken account of? By introducing a term called the fouling factor. And then we spent a lot of time talking about the 2 methods for analyzing the thermal performance of heat exchangers. What were the 2 methods? One method was the mean temperature difference method, in which we said there is a basic performance equation Q is equal to U A delta T m, and we derived expressions for the mean temperature difference in parallel flow, counterflow and cross flow. Cross flow again 3 cases. For parallel flow and counterflow we had expressions, for cross flow we had, based on numerical integration, we had graphs. We also discussed some special cases, the case of the m dot Cp going to infinity on either side. Then we came to the effectiveness NTU method. As another approach for solving heat exchanger problems. In this method, we defined the 3 dimensionless parameters. What were they? Effectiveness, capacity rate ratio C, and number of transfer units. And then towards the end, having defined these terms, we got expressions for the effectiveness in NTU. We derived expressions, effectiveness NTU relationships, effectiveness NTU relationships in parallel flow, counterflow, and presented results for the cross flow, the 3 cases of cross flow. For both the mean temperature difference and the effectiveness NTU method, we solved some numerical problems. Finally, just for a minute or two, I mentioned that there are other design considerations apart from the thermal considerations which went into our discussion, and these can often be just as important. So, with this we have come to the end of what we would like to do with the topic of heat exchangers.